this is a product, okay, because these two are series. Into, in a similar manner I can write. So we can find out the coordinate. We have a diagrammatic representation. We can come up with a sort of an algebraic representation for this structure. Okay. So now you can have components if it are like simple series or parallel. We know how to write it and then write down the structure functions. But there can be a complicated way in which they can be related to each other. We will take one simple complication and from that we will try to generalize. Like this. The structure function is like this. Again, you are all familiar with this kind of circuits. Okay, we call it as the bridge circuit. Bridge circuit, like Keystone Bridge. So here we would like to write down some way in which we can write down the structure function for that. Okay. So how is it that we can write? Then if one, let's look at the case when if 1 and 4 are working together. I am looking at a case when psi of x is equal to 1. If we have an expression in which one term will make that one as 1. Right? Will make that as 1. Okay? So if 1 and 4 is working, I think the system will be working. Or can you tell any other way in which the system will be working? 2 and 5. Or 1, 3, 5. This way, even if 2 and 4 is a failure, doesn't matter. 1, 3, 5. And another is 4. If I have a condition that I am dividing into few sets, that if one of them, okay, each one is sort of a subsystem. If the structure function of this subsystem, okay, where 2 and 5 are in series, that I am looking at a subsystem. If that subsystem is working, then this overall system will go. I only want I have 4 subsystems conceptually. If one of the subsystem is working, the component system will go. Okay. So I can view it as a parallel system. Each one is one of these sets. In each of these sets, the components are in series. So this way I can write it. As far as the computation of the structure function is considered, this and this are equal. I'm not trying to tell that both these circuits will work. In the case of electrical circuit, it may have a different way of working, functionality and so on. I'm not talking about this. This actually is a way of telling the indicator function of the system as a function of the indicator function of the components. So both these are the same diagrammatic representation of the structure function, psi of x. So what we are trying to do is that if you have any complicated diagrammatic representation of structure function, it's possible to come up with a structure function which is a parallel version of subsystems in which each one is a series. It's a parallel combination of systems in which each one is a series system. Then there should be a dual for that. It is also possible for you to come up with a case where you have a series of parallel systems. So any structure function, it should be, there is sort of a theorem, should be possible to convert it in two modes, either this mode, parallel version of series systems, or a series version of the parallel system. To this one we are going to introduce, make it a little bit more formal. One is called as the paths, and then you define it and then tell it as minimal paths. So if you have xn and it's a diagrammatic one, by path it's in a basically a graph. What we are trying to tell is a path set is one, that there exists a path from the input point to the output, okay, which is a sequence of the edges. Each edge will correspond to a component, such that all the components along the path, all edges along the path, if the components are working, then the system will be working. That is a path. And the minimal path is one. The path is such that if the path is working, what we mean by path is working is all the components which represent the edges of this one are working, the system will be working. But even if you remove one of the components, the one of the component fails, then the path will fail, and therefore the system may fail because of this. So that is called as the minimal path. So you will call, let us say P1, you can come up with P1, P2 and so on. Certain number of paths. There can be n component, but the number of these minimal paths can be much, it need not be n, it may be some other, such that each of this one, P1, okay, is the system will fail. One. Even if one of its path is functional, minimal path is functional, the system will be functional. So even if one of the path is functional, that is either if 135 alone is functional, or 234 or 14, that way then the system will be. So that way you can always find the minimal path set. Each one is called as the minimal path set. Which is a family of these sets. Then once we identify this one, then the diagrammatic representation of the structure function is nothing but it is a parallel version of the series, that each series corresponds to one minimal path set. 1, 4. Then we have another thing, minimal cuts. So here what happens is you are looking at a case, if you can identify a set, okay, such that if the set is not working fully, then the system will never work. That is what we mean. It cuts the connectivity from input to output. But all the elements or components in that set should not be out. Then we say that the cut set itself is not working. If the cut set is not working, the system will not work. Okay? Or if you can identify many such minimal cut sets, the system will work only when all the minimal cut sets, okay, is working. A minimal one cut set will be working even if one of its component is working. So we can divide it into C1, C2, C3, which are all minimal cut sets, such that psi of C1, that is, if we view each one of them as a subsystem. That is why we can define a structure function of the cuts. Okay, will be that at least one of them should be working within this cut. So if Ci has got some combination, okay, x1, x2, xg, and so on. Some components correspond or present in Ci. Okay, so you look at at least one of them should be working. That is, what is the condition for at least one of them should be working? Maths. We insist that all these cut sets should be working. That is why you have multiplied on these things. For each one of them, one of its component in the cut set has to work. That's all. We will look at now the bridge function. You tell me one cut set, in the sense which has certain components. Okay? If all those components fail, system will should not work. And tell me minimal such set. That will isolate the input and output. Some group of components that will form one cut set. 1 and 2. If 1 and 2 are removed, the system will not work. Similarly, 4 and 5. It's not only these things. Okay? It is also 1, 3, 5. If 1, 3, 5 goes away, then the system will not work. All of them, if it goes away, the system will not work. Similarly, 2, 3, 4. Then I can rewrite the structure function as follows. Okay, so we can either using the concept of minimal cut set or minimal path set to convert any structure functions in terms of series of parallel systems or a parallel of series systems. Once we know how to do this one, we can always write the expressions for this. What will be the expression for this? This will be For parallel it is max, right? Yeah, max. So like that we can always write. Again, if you want to go further, 1 minus of 1 minus, like that you can keep it and then write a big expression. So you can always write it in. Now, so far it's all about the indicator random variable and so on. Suppose you associate for each component, okay, not the state like indicator random variable taking 1, 0 based on the working of that one. You want to know, at any given time you want to tell what is the probability that the component is working. Okay, so we can associate with every component, okay, a probability that is working. Then obviously it means 1 minus PA means it's not working. Then if we can now define, okay, similar to this one, then we say that this tells you about the reliability of the component. Reliability of the component. The probability of the component is working. Okay, if it is more, then it is more reliable. If it is less, it is less reliable. So we can view it as a measure of the reliability. Similarly, for the entire system, you can tell about the reliability of the system, which will depends upon the reliability of individual components. So it will be a function of the P vector, where P vector is P1, P2, and Pn, the probabilities of working of the components on Pn. Then to find whether the R of P, okay, the reliability of the entire system, what you have to simply do is you have to substitute in the structure function the probabilities. Wherever you have got x1, x2, x3, the indicator random variable, if you substitute the probabilities, you will get the reliability of the entire system. That is, if you have a series systems, the R of our series it has to be the same expression, okay, for what the structure function is. Then you may have systems which is not so easily representable. For example, you may have k out of n system, which is very generic. Something which is more popular is called as the triple modular redundant system. expects that we have identical components, 3 of them, at least 2 of them should be working for the system to work. That's called as the triple modular element. Here it is k out of n systems. So how do we write the structure function of this one? For k out of n, so it is otherwise. So, or if it is triple modular, it is easy to find out. There are 3 systems, 3 components, 1, 2, 3, and if 1 and 2 together fail, the system will go 1, 3, 2, 3, and of course 1, 2, 3 together it will go 8. So we can immediately write down the one that so these are all yeah, this is of 1 minus of or what it means is, this is like this one. What is it? This is like a parallel system. Okay, I think that this, I am not sure whether this has to be put or even if this is there, it is. Okay. That is, it is a pair. If 1 and 2 is working, then system is working. 2, 3 are working. If all 3 are working, then of course all of them will be working. So this way you can have a k out of n system representation. Then we also recall we discussed about the hazard function. Okay, that is probability that that x is the lifetime of a system, lies between x and x plus dx. Given that x is greater than that x is the lifetime, conditioned that it has survived till a time x, what is the probability that it will survive for the next time interval of duration dx? This is what? This is the fx of x dx divided by this one. What is this? This is 1 minus fx of x. This is called as the hazard function. And so this can be written as right? I can write it like this, because this is 1 over fx of x, and then if I differentiate it, I will get this one will give you fx of x dx with the minus sign. So that is why I put a minus. So that is it. Now if I do an integration from 0 to any time t, so here I will have minus. So I can we have to sorry, it is a d minus d. That is what I was wondering. I can write it as d of this. So the d goes away. So I only have log of 1 minus of x of x between 0 to. So we get. So if I put this one, it is if I put 0, then it is the fx of x computed at 0 is what? This is 0. 1 minus 0 will be 1. Log 1 0. So that will be 0. At the here it will be 0, and here it will be. So I can write it as this. We have already derived it actually. So minus of I can put this. I can write it as the complement to distribution, which is given as usually L2. So e power of minus 0 to e h of x dx. So the this hazard function is related to the complementary CCDF using this formula. So we will stop at this point. There are a few more things.